Hello everyone, I am Dr. Gitumoni Sharma, Associate Professor, Department of Mathematics, USTM. Today I am going to take a class on special theory of relativity. Today's my topic is transformation equation for velocity and Einstein velocity addition theorem and its application. Let me talk first about the keywords of my lecture. Keywords are transformation equation of velocity, Einstein velocity addition theorem and its application. So, first I am going to discuss in details about transformation equation for velocity. We know that there are two frames always considered, one is at rest S frame and other is moving frame S dash frame with a constant velocity v. Let us consider a particle which has coordinate x, y, z, t with respect to S frame and with respect to S dash frame it is x dash, y dash, z dash and t dash. So, in relativity as I discussed in earlier classes, two frame always consider, one is rest frame, another is moving frame with a constant velocity. And now in this case we have considered a particle which has coordinate x, y, z, it is space coordinate according to the frame rest frame S frame and x dash, y dash, z dash according to the frame S dash. So, these are the two coordinates of this particle and particle is moving. This black color circle is assumed as a particle and S is frame, S dash is moving frame with a constant velocity. Let us assume a particle is moving with velocity v with respect to S and v dash with respect to S dash. So, their corresponding time are t and t dash. So, if this particle is moving then obviously it has velocity and then we get velocity transformation equation. Now, the velocity of the particle with respect to S frame, that is rest frame, it is considered as capital V and with respect to S dash frame it is considered capital V dash. Now, we are going to find a relation between v, v dash and small v. So, velocity transformation equation is capital V dash is equal to dx dash by dt dash. All of you know that velocity means rate of change of displacement. So, here v dash it is the velocity of this particle according to S dash frame. So, v dash is equal to rate of change of displacement. So, in according to S dash frame displacement is x dash. So, we write v dash is equal to dx dash by dt dash. Now, we apply here the Galilean transformation equation as we discussed earlier about Galilean transformation already derived, you know it. So, Galilean transformation equation is x dash is equal to x minus vt, y dash is equal to y, z dash equal z and t dash equal t. So, apply here a Galilean transformation. In place of x dash we put here x minus vt. So, we get d into x minus vt divided by dt. Now, dx by dt minus v constant. So, the moving frame moves with a constant velocity v. So, v constant. So, v remains same and t with respect to t derivation 1. So, we get dx by dt minus small v. So, again dx by dt it is the rate of change of displacement according to S frame, that is why it is capital V, because we consider the velocity of the particle with respect to S frame it is capital V. So, we get a relation between the capital V dash capital V minus capital V and small v. It is known as velocity transformation equation. This is velocity transformation equation. When velocity of moving frame approaches to speed of light, then Lorentz transformation equation is applied. So, these are x dash is equal to x minus vt divided by root over 1 minus v square c square, y dash equal y, z dash equal z and t dash is equal to t minus vx by c square whole divided by root over 1 minus v square by c square, given equation number small a. Similarly, in converse equation we get x is equal to x dash plus vt dash divided by root over 1 minus v square by c square, y is equal to y dash, z equal z dash and t is equal to t dash plus v x dash by c square whole divided by 1 minus v square by c square. Given equation number is small b. So, these are the Lorentz transformation equation. Now, there is a question, what is the difference between Galilean transformation equation and Lorentz transformation equation? As you know that Galilean transformation equation considered for less velocity. When velocity very less than in comparison with the speed of light, then applied Galilean transformation equation. But when velocity of the moving frame approaches to speed of light, then consider the Lorentz transformation equation, and in this situation only Lorentz transformation equation is applied. So, this is given by equation number A and B. So, where velocity very less than c, then you see that v by c, this ratio is negligible, and so the Lorentz factor 1 by root over 1 minus v square by c square, it is known as Lorentz factor, and this factor is negligible in case of velocity very less than c, and then Lorentz transformation equation convert to Galilean transformation equation. So, now what we do here, we take the derivation of the Lorentz transformation equation, then we get dx dash is equal to dx minus v dt divided by root over 1 minus v square by c square, equation number 1, and similarly dt dash is equal to dt minus v dx by c square divided by root over 1 minus v square by c square, equation number 2. Here simple calculation here, so not mentioned in this slide, only written the result dx dash and dt dash. Now, dividing equation 1 by 2, we get that dx dash by dt, dx dash by dt dash, and it is we know that it is rate of change of displacement, and if as here displacement only x direction, so it is the velocity component in x direction, and it is denoted by u dash x. Dash quantity means it is according to the moving frame, according to the s dash frame. So, we write here u dash x is equal to dx dash by dt dash. Now, here dividing dt dash, we get dx minus v dt divided by dt minus v dx by c square, simple calculation here. Again we after dividing each term by dt, we get the dx by dt minus small v divided by 1 minus v by c square dx by dt. Now, again we get the term dx by dt, again it is the rate of change of displacement, and it is the undressed quantity. So, it is with respect to s frame, rest frame. So, we write here dx dt, it is symbolized by ux minus v divided by 1 minus v by c square ux. So, it is equation number 3. Now, again differentiating y is equal to y dash, z is equal to z dash, we get equation 4 and 5, and it is dy dash is equal to dy, dz dash is equal to dz, simple calculation. Again now, if we divide equation 4 by 5, then obviously we get dy dash by dt, and dy sorry, here one mistake, dividing 4 by equation 5 given, but we divide this term dy dash by dt dash. So, then we get u dash y, and it is dy into root over 1 minus v square by c square divided by dt minus v dx by c square. Now, simplifying we get uy symbolized for dy by dt, then we get the equation number 6. So, we find u dash x and u dash y. It is velocity component in x direction and velocity component in y direction. Similarly, same procedure, similarly we find u dash z, it is velocity component in z direction. So, u dash z, it is given by equation number 7, and same procedure we find the velocity component in z direction. So, equation 3, 6 and 7 are the transformation equation for u dash x, u dash y and u dash z. In case of Galilean transformation or in case of less velocity, then we apply Galilean transformation, and then we have the velocity transformation equation is v dash is equal to v minus v small v, we just derive. And now, in case of velocity approaches to the speed of light, then we get the three component ux, u dash x, u dash y and u dash z. Repeating the same operation, we get ux, uy and uz. So now try to understand what is difference between ux, uy, uz and u dash x, u dash y and u dash z. So ux is the velocity in x direction according to s frame, and u dash x velocity in x direction according to s dash frame. Similarly, uy velocity component in y direction according to s frame, and u dash y velocity component of the particle in according to the s dash frames. And again same procedure we follow in case of the uz and u dash z. So it is given by equation number 8, 9 and 10. Now another important topic I am going to discuss, it is Einstein velocity addition theorem. Now where Einstein velocity addition theorem is applied, in case of a moving particle or in case of Galilean transformation, in case of Lorentz transformation, it is no problem, we get the velocity addition theorem simply. But when we consider this type of problem, that a spaceship we consider and one observer on earth, he is observed the spaceship in this situation, that spaceship is moving with a velocity capital V, and another person in this spaceship, he observed that a ball in his hand, when he throw this ball, then ball is moving with a velocity small u. Then two velocity here consider, spaceship velocity V and the ball velocity under the spaceship, it is u. Then the observer on the earth, on the ground, what he get in this situation when the both velocity is very large, approaches to speed of light. So in this case Einstein velocity addition theorem applied. So here suppose an object is moving with a speed u in s along the x direction, then ux is equal to u. Ux means velocity component in x direction, it is considered u, and other two component uy and uz 0, because they are y and z directions are parallel, so they are 0. Correspondingly in s dash we get the u dash x is equal to u dash y, and other two component will be 0, the u dash y and u dash z will be 0. So we get the u is equal to u dash plus v, we get from equation 8, equation number 8c, ux is equal to u dash x plus v divided by 1 plus v u dash x by c square. So from this equation simplifying, we get u is equal to u dash plus v divided by 1 plus v u dash c square. This equation is known as Einstein velocity addition theorem or relativistic Einstein addition theorem. So this formula we can apply in case of light particle. If we put u dash is equal to c, c means speed of light particle, then we get that u is equal to c plus v divided by 1 plus v c by c square. So simplifying, we get c. So velocity of the particle is a light velocity. This is indeed expected from the principle of universality of C. So already principle of relativity says that all physics law must be same in all inertial frame, and another principle of special relativity is that speed of light is universal constant. So this is already expected, this law already expected from this example. Suppose another this slide only for our concept, already I explained in this previous slide. So suppose two person A and B, A is standing on the ground and B is spaceship, velocity of spaceship 500 meter per second. According to A, velocity of the ball throwing by B is 50 kilometer. Then according to A, the velocity of the ball 500 plus 50, so total 550 meter per second. So see here, velocity of the spaceship according to the observer, it is 500 meter per second considered, and ball velocity is 50 meter per second. Then according to the person on the earth, he says that ball velocity is 550 meter per second. Then according to A, the velocity of the ball is 5 50 meter per second. The velocity of the ball according to A is 50 meter per second. So, but it is happen only in case of classical mechanics, when both speed of spaceship and ball very high, then its velocity v plus u divided by 1 plus vu by c square. So, it is Einstein velocity addition theorem. So, when velocity is very high, it approaches speed of light, then Einstein velocity theorem applied. Now, some brief history here given, a velocity about the Einstein velocity addition formula. So, a velocity addition formula is an equation that specify how to combine the velocity of object in a way that is consistent with the requirement that no object speed can exceed the velocity of light. Such formulas apply to successive Lorentz equation. So, they also relate different frames. So, here given when velocity Einstein velocity addition theorem applied. Accompanying the velocity addition is a kinematic effect known as Thomas precision, whereby successive non-collinear Lorentz would become equivalent to the composition of a rotation of the coordinate system and a boost. Standard application of velocity addition formulas include the Doppler effect, Doppler navigation, and the aberration of light and the dragging of light in moving water observed in the 1851 Fizeau experiment. So, Einstein velocity addition theorem in Fresnel drag effect, Doppler effect, aberration of light, so many application of Einstein velocity addition theorem. The notation employs u as a velocity of body within a Lorentz frame S and v as velocity of a second frame S dash as measured in S, and u dash as the transform velocity of the body within the second frame. Then we can also by with this variable we can see that the Einstein velocity addition theorem. The speed of light in a fluid is slower than the speed of light in vacuum, and it changes if the fluid is moving along with the light. In 1851, Fizeau measured the speed of light in a fluid moving parallel to the light using an interferometer. Fizeau's results were not in record with the then prevalent theories. So, these are the brief history about the Einstein velocity addition theorem. Fizeau result led physicists to accept the empirical validity of the rather unsatisfactory theory by Fresnel that a fluid moving with respect to the stationary ether partially drags light with it, that is the speed is c by n plus 1 minus 1 by n square into v instead of c by n plus v, where c is the speed of light in the ether, n is the reflective index of the fluid, and v is the speed of fluid with respect to ether. So, later we discuss one application of Einstein velocity addition theorem, that is known as Fresnel drag effect, and this is the result of Fresnel drag effect. The aberration of light, of which the easiest explanation is the relativistic velocity addition formula, together with Fizeau's result triggered the development of theories with Lorentz ether theory of electromagnetism in 1892. In 1905, Albert Einstein, with the advent of special relativity, derived the standard configuration formula for the addition of relativistic velocities. The issues involving ether were gradually over the years settled in favor of special relativity. So, these are some brief description of Einstein velocity addition theorem. Now, we are going to discuss about the application of Einstein velocity addition theorem. This is known as Fresnel drag effect. So, before discussing Fresnel drag effect, I am again want to say about the Michelson-Morley experiment. This is the same type of experiment, already Michelson-Morley experiment discussed in our previous classes. Michelson-Morley experiment is here I given the picture both Michelson-Morley experiment and Fresnel drag effect. In Michelson-Morley experiment only 2 mirror considered, but in Fresnel drag effect considered the 4 mirror M1, M2, M3 and 4. In case of Michelson-Morley only 2 mirror considered M1 and M2. Then monochromatic source is taken in both experiment. Then in Michelson-Morley experiment, another important things considered, that a glass considered here, so that light partly reflected and partly transmitted. But here considered in this experiment considered a glass tube where water is filled, and this glass tube consider, and the light beam passes through the water. And another difference between the Michelson-Morley and this physics experiment, it is that here light considered and light are reflected and transmitted, then they are recombined at O and then observed by telescope. But in physics experiment, the light beam passes through the 4 mirror, and they are after one is rotated through clockwise direction and another is rotated anti-clockwise direction, and one is rotated through the direction of the water and another is rotated through the against the direction of water. Then they recombine and then observed by telescope. So that is the major difference between Michelson-Morley experiment and the physics experiment, and they result almost same, both same, and they say that it are not exist. So an effect called the Fresnel drag effect was predicted by J. A. Fresnel in 1817 and was confirmed experimentally by Fizeau in 1851. So it is given by Fresnel, J. Fresnel in 1817, and this experiment confirmed by Fizeau. So it is known as Fizeau's experiment also. From velocity addition theorem, Fresnel drag effect can be explained. In the conventional Fresnel drag effect, moving matter drags light, imparting an extra speed to it. Measured by Fizeau in 1851, Einstein noticed that it is a relativistic effect and that the speed of light in the medium can be calculated from Lorentz velocity formula. A moving medium, some history of physics experiment given. A moving medium drags light along with it as measured by physics and explained by Einstein's theory of special relativity. Here we saw that the same effect can be obtained in a situation where there is no physical motion of the medium. Modulations of both the permittivity and permeability faced in space and time in the form of travelling waves are the basis of our model. Space-time metamaterials are presented by effective bianisotropic parameters which can in turn be mapped to a moving homogeneous medium. Hence, these metamaterials mimic a relativistic effect without the need for any actual material motion. We discuss how both the permittivity and permeability need to be modulated to achieve these effects, and we present an equivalent transmission line model. So, this is the brief history about this effect, Fresnel drag effect. This is the picture. O is monochromatic light, M1, M2, M3, M4, these are 4 mirrors. This is the glass tube and water flows in, and water in the lower arrow direction, and water flows in the direction of V, and then water flows out in the top of the tube. From top of tube, and from the monochromatic light source, a light splitted the mirror M1 and it 1 and 2 into 2 ray, then 1 ray passes through the water and to M2, then M3 and then M4, and finally again back to M1, and ray 2, here description given. light from a monochromatic source O falls on a partially silvered mirror M1 which splits on the incident beam into two beams. One beam denoted by 1 passes through flowing water to mirror M2. On reflection from M2 proceed to mirror M3. On reflection from M3 passes through flowing water again to mirror M4 and finally through M1 to the telescope. Then these beams follow a counterclockwise route. So, this the description here written. Again the other beam denoted by 2, this beam denoted by 2, it is anti-clockwise direction. So, follows a anti-clockwise route M1 to M4 to M3 to M2 and finally back to M1. So, interference fringes due to the optical path difference between the two beams would be seen in the telescope. So, at last the telescope the observer observed by the telescope the difference between the ray 1 and ray 2. What is the path difference? What is the path difference or time difference between ray 1 and ray 2? Water flows with a speed v as shown in figure through two tubes fitted with glass plates at their ends. The first beam travels in the direction of water flow and the second beam travels against the direction of water flow. So, let us consider the experimenter as the S system and the flowing water as the S dash system. So, always we consider two frame S frame and S dash frame. So, S frame is rest position and S dash is moving with a constant velocity. So, here we consider the S frame is the experimenter who is experiment the system, then it is S frame, and the flowing water it is considered as a S dash system. Then C is the speed of light according to S and C by N is the speed of light according to S dash. So, N is the refractive index of water. Now, using equation 11 from earlier slide, we get the equation number 11 and simple calculation here we find that U dash is equal to C by N using equation number 11. Then according to S frame, the speed of light in flowing water for the beam 1 is given by U1 is equal to U dash plus V. It is simple calculation, U dash plus V divided by 1 plus U dash V by C square is equal to C by N. In place of U dash we write C by N plus V divided by 1 plus V by NC. After calculation we get C by N plus V into 1 minus 1 by N square. So, it is in case of the beam 1. Then the corresponding formula for the beam 2 is after calculation this same calculation, same procedure, we get the U2 is equal to C by N minus V into 1 minus 1 by N square. Now, try to understand, try to see the difference between U1 and U2. U1 is the velocity of the beam 1 and U2 is the velocity of the beam 2. Then we get C by N, first term is the same in case in both ray, but second term V into 1 minus 1 by N square is second term also same. Only the difference is first is the plus sign in between both term and second is the minus sign. If we consider V is equal to 0, velocity of the V means what? Velocity of the water. If we consider the water is a stationary state, then V 0, velocity of the water 0, then U1 and U2 both will be C by N, then both will be same. So, these fringes are produced due to the difference between the two speeds U1 and U2 and these fringes were observed by physio. The fringes disappear if the water is stationary, that is V is equal to 0. So, it is called the Fresnel drag coefficient and 1 minus 1 by N square is known as Fresnel drag coefficient. So, Fresnel drag effect boosted up the ether theory. So, already ether theory we discussed and how ether not exist for that we saw that Michelson-Morley experiment. So same type of result we get here, but the special relativity does not allow the existence of ether. Obviously, the derivation of equation 12 and 3 from Einstein velocity addition theorem confirms further non-existence of ether. So it is the Fresnel drag coefficient. We see that how velocity of water will be 0 in case of Fresnel drag experiment. Today in today's class we discuss about the transformation equation of velocity for a moving particle in case of high velocity, in case of low velocity, and we consider Einstein velocity addition theorem or relativistic addition theorem and its one application. It is known as Fresnel drag coefficient, Fresnel drag effect and Fresnel drag coefficient. Thank you.